Hi, everyone. Welcome to our presentation. We'll be discussing our paper on decentralized multi-agent reinforcement learning via distribution matching. This is joint work by Caroline, Wang, Ishan Durukar, myself, Elad Liebman, and Peter Stone. We're from the Learning Agents Research Group at the University of Texas at Austin. I'm also a member of the research lab at Spark Cognition. And let us begin. So the high-level motivation, of course, is that reinforcement learning is challenging for a single agent, and it is substantially harder when multiple agents are learning at the same time. And one of the key reasons for this challenge is that when agents learn and act simultaneously, then them changing their policies makes the environment inherently non-stationary. We are considering a specific case of cooperative multi-agent reinforcement learning versus rather say competitive, where you have multiple agents competing with one another. We are considering a case where you have multiple agents which are trying to achieve a shared goal, or at least coordinated goals. So far, most solutions to this setting have been either relying on fully centralized learning, which in effect reduces the problem to single agent learning, or using what's called centralized training, decentralized execution, or CTDE, which has been probably the most dominant approach to multi-agent reinforcement learning in recent years. One of the issues with these two approaches, either fully centralized learning or CTDE, is that they require agents share model components and communicate with one another, which oftentimes is not practical even in training time. And therefore, in our work, we propose a different approach, which is we want to focus on fully decentralized learning, i.e., agents learning without sharing model components or explicitly communicating with one another during training or execution. And this is relevant in a lot of use cases, such as search and rescue robotics, autonomous driving. If you want to basically, in a say lifelong learning scenario where you have multiple agents which need to adapt to new tasks all the time, in terms of scalability, you can't afford to basically have them retrain centrally for every new task that you face. And of course, the ability to parallelize, have same agent manage multiple tasks at once with varying teams, etc. So the key question that we are tackling in this paper is, how can we foster team cooperation, i.e., striving in a coordinated fashion towards a shared goal in the decentralized learning scenario without explicit communication or being able to share model components, etc.
Okay, now I'll quickly give a quick background on the settings that we are dealing with here, and then give a short overview of our method before we head to the experimental section. For the background, let's start with stochastic games. So the stochastic games are a generalization of the Markov decision process, which is used to train reinforcement learning agents, or which is used to specify the setting in which reinforcement learning agents operate. In a stochastic game, you instead of a single agent, you have k different agents. The state is still fully observable, so all agents can see all the other agents and the full state that they're dealing with. The action space is now divided into k components. Each agent can take actions with respect to its action space, and then the concatenation of all these actions is presented to the environment, which causes a transition into a new state according to the transition function. The initial state is sampled from an initial state distribution, rho sub 0, and depending on the setting, you have reward functions per agent that can be the same if it's a fully cooperative setting, or can be different depending on what the task is. And we leverage this like separate reward function in our method a little bit. And finally, as in the single agent reinforcement learning setting, we have the discount factor gamma, which lies somewhere between 0 and 1. And this discount factor basically tells the agent how much to prefer rewards that are that exist closer in time rather than ones further away. Each agent has its own policy, pi sub I, which is a mapping from the state to a distribution over its actions. And all the agents take sample actions according to their own policies, and the concatenation is presented to the environment. Next, the other component that is important to our work is distribution matching. Distribution matching is one approach to imitation learning, which has gained a lot of popularity in the recent years. When I discuss a distribution, I'm basically talking about the agent state action visitation distribution, which is the distribution of states and actions that an agent experiences when it starts executing its policy and holding the other agent's policies, which is indicated here by pi sub minus I constant. So we freeze the other agent's policies and we execute agent I's policy, and then we consider the states and actions that it has visited. The main idea behind distribution matching is that when we learn a policy that matches these distributions exactly, then it will lead to imitating the demonstration policy. The contributions of our work are to use the idea of distribution matching to encourage coordination between agents. So we basically give each agent demonstrations from coordinated experts, and then each agent independently tries to perform distribution matching with respect to its expert policies. And this distribution matching process should lead the agents to coordination themselves. In service of this idea, we show that the expert policies are a Nash equilibrium for this distribution matching problem, which is an independent imitation learning task. And finally, we empirically evaluate our idea on the StarCraft 2 environment and show an empirical improvement with respect to independent policy gradient when using this distribution matching approach. Let's go into this idea in a little more detail. So on the left is an illustration of our approach. At the bottom, we have our K agents, each having their own policy, pi sub I to pi sub 1 to pi sub K. They're presented with the environment reward, which we consider a single cooperative reward where each agent is trying to accomplish the same task. And on top, we have the expert policies, pi sub E1 to pi sub E sub K. And we use these expert policies to generate demonstration distributions. And then the agent also simultaneously tries to match these demonstration distributions using the distribution matching techniques, such as GATE. In our theoretical analysis, we show that these expert policies that are indicated on top constitute a Nash equilibrium for the distribution matching task that each of these agents are trying to perform. And when we mix these distribution matching rewards with the shared task reward, which gives us a mixed reward, these expert policies also constitute a Nash equilibrium in that mixed reward setting. This is a brief overview of our algorithm. I won't go into a lot of details over here, except to say that to kind of highlight the innermost loop where we sample M states from each agent's demonstration. We update the discriminator, and then we perform, we get the reward from this discriminator, which is these two steps are the Gale steps. And then the agent gets a mixed reward of the environment reward plus this Gale reward times some constant to kind of mix them appropriately. And then the agent updates its policy with this mixed reward. And this is basically independent reinforcement learning with the mixed reward that is indicated here on the screen. Now Caroline will go over the experiments that we perform.
Okay, so yeah, in our experiments, each agent is learning independently with PPO, which we'll refer to as IPPO in this talk. The demonstrations are sampled from each of K experts, each of whom were trained on the original environment reward using IPPO. And in our method, each agent is trained to maximize this mixed reward that consists of the environmental reward corresponding to the task, summed with the Gale reward. So the experiments are conducted on cooperative tasks from the StarCraft-2 domain. In this domain, the general goal is for the multi-agent reinforcement learning algorithm to control a team of allies to defeat a team of enemies controlled by a game AI. And the two tasks we're considering are 5v6 and 3v4, where the first number is denoting the number of allies and the second number shows the number of enemies. And we consider two baselines. The first is IPPO with the environment reward alone, which is our decentralized baseline. And then the second one is QMix with the environment reward alone, which is our CTDE baseline. And we would expect the CTDE method to be a reasonable upper bound on the performance of our decentralized method. So in these plots, the learning curves of the IPPO and QMix baselines are shown. And the metric is the mean battles won against the enemy team. So we test our method on two qualities of expert demonstration. The first demonstration quality achieves about a 30 to 40% win rate, which is well below the performance of an optimal policy in this task, but nonetheless, our method is showing significant improvements in learning speed on both tasks and a significant improvement in asymptotic performance in 3b4. We see a similar result with the second demonstration quality, which is about 20% better than the first demonstration. Both runs of our algorithm learn more efficiently than the IPPO baseline. And as expected, we see that QMix is an upper bound on the performance of all the algorithms here. So despite the 20% difference in win rate between the two demonstrations, our algorithm achieves similar learning efficiency. And this motivates us to kind of invest the robustness of our method 2 demonstration quality in this next experiment. So on this set of graphs, the QMix baseline is shown in red again for reference, and the demonstration qualities are shown with horizontal lines. The performance of our algorithm with the lowest to highest demonstration qualities is plotted from tan to dark green for both tasks, where tan is the lowest quality of demonstration and green is the highest. And then for both tasks, we observe that there's a sudden jump in performance after a certain threshold, indicating that the demonstration should have some minimal win rate to be useful to our algorithm. But beyond that, our method is relatively invariant to the demonstration quality. So this shows that the demonstrations aid learning by providing a useful cooperative signal that enable agents to coordinate and therefore discover higher reward behaviors. So in this experiment, motivated by the last one, we asked the question, in what sense should expert demonstrations be coordinated? We identified two potentially relevant axes. So first, the demonstrations could be concurrently sampled, meaning that the K sets of demonstration trajectories are collected simultaneously from K experts acting together in the environment. The demonstrations could also come from co-trained expert policies, which mean policies that have been trained together to cooperate at and succeed in the desired task. So our method relies on demonstrations that are concurrently sampled from co-trained expert policies, while the others could be considered ablations. And we study all four combinations on the 5v6 task to identify which are most significant. So in this figure, our method is in blue, and the left plot is with the lower demonstration quality and the right plot's with the higher demonstration quality. And we find that the demonstrations being currently sampled is not an important variable, while on the other hand, it's a lot more important for the demonstrations to come from co-trained expert policies. Thank you for listening, and if you have any questions, please come to our scheduled time on Google Meet.